Good. So then let's move to our first speaker of this session. It's Leonid Mytnik, and he will present on the speed of a front for a stochastic reaction diffusion equation with non-Lipschitz drift. So please, Leonid.
Okay, thank you. Just a second, I'll do the sharing. Okay. Good. First of all, thanks a lot to organizer for giving me an opportunity to give a talk at this great meeting. Indeed, I enjoy the talks here. Very, very, very nice. So the talk on the speed of Frank propagations for stochastic reaction diffusion equation. This talk is based on joint papers with Karl Müller, Leonia Ryzik, and two great postdocs at the Technion, Clayton Barnes and René Aussan. So we'll start with the deterministic reaction diffusion equation, and it's a famous Fisher, Kolmogorov, Petrovsky, Piskunov equation, or we'll denote it FKPP or just KPP equation, which is the nonlinear parabolic equation. So this is function u depending on time and space. Space is real line, and the first derivative of u is the half second derivative in space, first derivative in time, plus the drift, or sometimes it's called reaction term. And the drift is u times 1 minus u, and we consider the solutions that take values between 0 and 1. A few words about the motivation, which come from biological consideration. If one have a population which the rate lives on R, and UTX is proportion of a population time t at site X with an advantageous gene. Members of population move at random, and this gives rise to this term, which is half Laplacian, so comes from Brownian motion. And more fit members of population replace less fit, and frequency of interaction is proportional to the product of the number of members of population which are fit and unfit, which gives rise to this term in the equation. Okay, the number of fit population is increasing. Okay, and a few words about the solutions to this equation. There are a special class of solutions which are called traveling wave solutions, and they look like this. UTX can be represented as UC x minus CT. This is a traveling wave solution, which in fact is a graph of this, which travels to the right. With speed c. So the family of such solution is parameterized by speed c, with which it can go. So for each c where there is solution, so UC is supposed to solve this differential equation, and for all c for which solution exists, we have this traveling wave solution, which is 1 at minus infinity, 0 at plus infinity. The picture here is a bit misleading. It looks like a solution equals to 0 here and it equals to 1 here. No, it's just very small. So it's positive everywhere and less than 1 everywhere, just getting very, very small to the right and very close to 1 to the left. Okay. Another one can also be interested in other solutions, not only traveling wave solutions, and mainly we are interested in the situation when the initial conditions for this equation will be initial conditions that we call conditions with the compact interface. So if this is level 1, then we talk about the initial conditions that have a left edge of the interface, let's say it's A0, the right edge is R0, and this is initial condition for our equation. It's 0 here, all the way here, 1 over here, and there is some interface, and we call it compact interface, or sometimes we call it compact support. It's just the same. And the question is, what happens with this equation, starting from these conditions, when time goes to infinity? And it turns out that there exists C star and the function mt, such that mt over t converges to C star as t goes to infinity. And if we look at the solution of this equation, starting from such initial condition at the proximity of mt, which move to the right with the speed c star, then this solution converges, in fact, to traveling wave solution with the speed c with this parameter c star, where c star is square root of 2. It is, in fact, the minimal possible speed of traveling wave solution for such equation. And one can also ask the question how MT looks like, and Bramson found out that there is a correction to the C star times T, which is this term, square root of T, and this correction is the universal constant times logarithm T. So this should be here, and there also should be a constant which depends on the initial condition. This constant is not universal; it depends on exact form of the initial condition. Just one remark. So in many cases, so many people consider this equation without without a factor of 1/2 frontal derivative. In this case, the minimal speed will be 2 without square root, so we'll have 2t here. Change a little bit also the constant here, but all the rest remains the same. It's just a simple scaling of the equation. The question we may also ask, what happens in the more general drift instead of reaction term, instead of u times 1 minus u, one might have f of u subject to some regularity conditions, and in such case, so the speed is square root of 2 times the first derivative of function at 0. Okay, and so just pay attention that if there is no the derivative, for example, infinity, it implies that the speed of propagation to the right of this equation is infinity. So in the case when we have a derivative, it's finite. So we get that mt is t times this factor, and ut propagates to the right with the speed c star. And so this is very important, whether derivative is finite or infinite. Okay. Now the question is, we would like to move to the stochastic version of the KPP equation, and we end this kind of multiplicative noise. We have some constant here, we have square root of u times 1 minus u, and here is the white noise. And so informally, the variance of the noise term at the proximity of the point tx is again u times 1 minus u times dx dt. Motivation is very similar. It also may come from biological world. So outcome of interaction between fit and unfit individuals may be random, and this gives us the rise to this noise. Interaction between fit and unfit individuals are independent at different space-time points. That's why the noise is white noise, which has independence between special, its values are independent at different space-time points. And the rate of interaction is proportional to u times 1 minus u, which gives rise to this multiplicative noise, and the variance should be proportional to u1 minus u. If variance proportional to u1 minus u, then here in front of noise you need the square root of u1 minus u. This is the reason why the square root many cases appears in this type of equations. Okay. And now, so we have this equation, which is now stochastic KP equation, and again we will be starting from the compact support compact interface initial conditions. So so we start something like this. So this is R0, this is R0, and the question you ask, so if this is U0, then whether compact interface property holds also when time propagates, when equation propagates with time, and it was shown by Carl Müller and Sowers in '95 that compact interface property holds for any time. We again have the compact interface property of the solution. So if solution propagates, then by time t you again see something like this. Yeah, so that again you will have some point like RT here. Sorry, LT, and which is the left edge of the interface, and RT, which is the right edge of the interface. Moreover, they showed that in fact the propagation of the right edge of the interface has a speed. Okay, there is v of sigma, which is limit as t goes to infinity of RT over t. So the speed of propagation of this right edge. And it was shown for small values of sigma. And then Colin during 2005 showed that in fact for any sigma, there exists a speed of propagation. And the question that we may ask, what depends the dependence of v on sigma? How the speed of propagation depends on sigma. So we know that v of 0, for example, equals square root of 2, since this is should be square root of 2, since this is this will give rise to the regular deterministic KPP equation. And the first question was what happens with this with the speed of propagation for small sigma? And in joint paper with Carl and Jeremy in 2011, we showed that for small sigma, the asymptotically v sigma behaves like this speed for sigma equals to 0 minus this correction, which is constant divided by log sigma square. Okay, and so as sigma goes to 0, this correction goes to 0, and we are left with this speed for deterministic equation. There also one more term here, and we know the order of this term, but not specific constant in front of this term. So, but I just like this, write the asymptotics until this first term after the speed at zero, speed of the equation for sigma equals to 0. In fact, this result verified Brunet and Bernard Derrida conjecture of '97, where they predicted exactly this term. In fact, also the next term was predicted, was also predicted. This type of one more remark, just pay attention that the noise, in fact, have a dramatic effect on the speed of propagation. One might expect that for small sigma, the speed will be changed by some sigma to some power function of sigma, and it turns out that it's much bigger. It's 1 over log. It's constant over log sigma square, which is much bigger than any power of sigma. So speed. So this noise indeed has a dramatic effect on speed. And the second remark, the adding of this noise slows down the propagation of the equation. So this correction is with sign minus, so the propagation slows down. So this kind of this noise some kind of has a killing effect on this equation at the tail, and we'll get to this back to this point later. What happens? So this gives asymptotics for sigma small. What happens with asymptotic for sigma large? Again, there is a result of Conlon and Doring that, in fact, V sigma, as sigma increases, the speed of propagation should decrease to 0, and they have a lower bound on the asymptotic of V sigma. So we get sigma squared times V sigma is greater or equal than 1 limit of this as sigma goes to infinity. So from below, V sigma is bounded by 1 over sigma square when sigma goes to infinity. And their conjecture was that, in fact, there is a precise asymptotic. V sigma behaves like 1 over sigma square. In fact, we verified this conjecture and talk about this again later in this talk. Okay, so so these are two types of asymptotics we are interested in for small sigma and for big sigma. So again, for sigma infinity, the speed of propagation is 0. For sigma 0, the speed of propagation is this square root of 2. Well, the question we ask, what happens if we replace this drift u times 1 minus u by more general drift? And the question is whether there is any motivation for doing this. And in fact, motivation before doing this, I give you another motivation to study this stochastic KPP equation, and it comes from branching coalescence system of Brownian motions. And this comes via duality. Consider a system of particles moving as independent Brownian motion. Each particle splits in two at rate 1, and pairs of particles at rate sigma square according to the intersection local time. So we have something like this. You have time 0. Suppose you start with one particle, it goes, it splits again, it splits again. But at a certain point, the particle, they come close together, spend some time, and with the rate of the intersection local time between the motions, they coalesce. So it's possible that this scenario that two particles coalesce at 1. And we are looking at if one looks at the position of rightmost particle in this branching coalescence system, call it RT-BC at time t, then there is a duality relation due to Shiga that gives the following expression for probability that the rightmost particle is greater than any number z. To calculate this probability, one can take the solution to this stochastic KPP equation with this drift, which starts with the Heaviside function. So if you take, so this is the initial condition for our equation, and ask what's the expected value of this solution point at time t at point z, and then this gives this probability, this duality. Okay, this duality relation, in fact, allows us to get the information on the speed of propagation of the rightmost particle in this branching coalescence system from the speed of propagation of the front of solution to this stochastic KPP equation. In particular, one can get the upper bound on the speed of propagation of this particle, and this upper bound will be given in terms of speed of propagation of u. And when you look at this duality relation, then heuristically it's clear one introducing the noise slows down the speed of propagation of u. Since if speed of propagation of u related to speed of propagation of this particle, clearly when we have the coalescence mechanism here, we have less particles than in the system without coalescence, which corresponds to the system without the noise, just branching Brownian motion, and it clearly propagates to the right at a slower speed than a system without coalescence. So it gives some heuristic idea why introducing, by this duality picture, one can get heuristic idea why more noise slows down. And clearly when sigma goes to infinity, so at any time when you have a branching event where two particles are born, the coalescence at rate infinity immediately make the coalescence event, which means so when sigma is infinity, we're left just with one Brownian particle here. Okay, and the speed of this particle is 0. Okay, this gives us another motivation to study stochastic KPP equation. And another remark: this drift term here has connection to the branching mechanism in a dual system, and this term, which is the noise, is coalescence. Okay, coalescence. Okay, and the question we ask: so if we change a little bit the branching mechanism, here is a binary. Every time particle branches into two particles, so then it give rise to another term, and it's exactly what we are saying. So we'd like to have to check what could be the duality for different function fu. And for this, let's take more general branching mechanism. Before, probability of having two offspring was 1, and there is nothing, no more options. We can take probability of having offspring to be qk and define function fu in this way. It's 1 minus u and minus the probability generating function at point 1 minus u, probability generating function of the branching mechanism. And if the first derivative equals to the mean of the branching minus 1 is finite, okay, if the mean of branching is finite, then it's easy to check that Shiga duality relation also holds for this system. And we conjecture that duality holds also when the derivative of function at 0 is infinite, and this brings us to the drifts which are not necessarily Lipschitz. And this also gives us a motivation to study it, since for special functions fu, which are not Lipschitz, we can relate the solution to this stochastic KPP equation to the branching coalescent Brownian motion, where the branching has infinite mean. And it's very interesting since in many situations, branching has infinite means, so the branching system explodes. And our conjecture that, in fact, in the case when you have coalescent mechanism, so it doesn't explode. And this this may come from the studying this equation. And another point is whenever f prime 0 is infinity, in the case when sigma equals to 0 and we consider the deterministic equation, the speed of propagation should be infinity of this KPP equation. If we can show that the speed is finite, it somehow again means that the noise has a dramatic impact on the properties of the KPP equation, introducing this type of noise. Okay, so let's try to study this. This equation with more general function. We start with a simple case where f is of the KPP type. So first thing is that derivative f prime 0 is finite, and you have this f0 equals f1 equals 0. So for example, u1 minus u is the typical example of function which belongs to this class. Okay, but there are many others which satisfy this. And in the same paper with Carl and Jeremy, we showed that for small sigma, the asymptotic of v sigma near 0, so with respect of v sigma for small sigma of the speed of propagation of the equation has the same expression. So nothing changed. So the only this asymptotic depends only on the derivative of function f at 0. So the form of the function not really important. And just one word about how this could be, how one can think about the proof of this. For small u, the noise in some sense wins the competition against the drift. So in which sense wins? It means so whenever u is smaller, say, than sigma square, one can show that in these regions, the noise very fast brings the solution to this equation to 0, which means that one compare this equation to the equation where the drift doesn't act for small values of u. So it's called the equation with cutoff, where they replace this drift to the drift fu times indicator that u is greater than sigma square. So somehow we say that noise doesn't, so that the drift doesn't have any effect for u smaller than sigma square. And it turns out for this deterministic equation, the speed indeed is given by this expression. Now we ask what happens in the case where f is not Lipschitz, not of KPP type, it's which say it's much more general. So we start this KPP with not necessarily Lipschitz f. Maybe Lipschitz, but not necessarily Lipschitz drift f. And the first question you ask, if it's not necessarily Lipschitz, whether there is existence and uniqueness to solution to this equation. And our first result in this paper, in the paper with Karl Müller and Leonie Rizhik, says that if you have the following bound on fu, so fu is bound by constant square root of u1 minus u, then there exists unique and law solution to this equation. And this, again, we have the compact interface property for this equation. And the solution has a speed v sigma, which is fine. Okay, just one remark. So this type of result follows for Dawson from so-called Dawson-Gersanov theorem, which allows us to eliminate this drift, and the solution to this equation without drift, we know, has a unique solution. and this allows us to get the unique solution to this equation. And this bound is exactly the bound that allows us to apply Dawson-Girsanov. This is follows more the argument of Conlon and Derrida. And now, so in this paper with Karl and Lenya, so we wanted to study the asymptotic behavior of the speed for such equation where for large noise, where sigma goes to infinity. And there's that under a little bit stronger condition of the function fu is bounded by u1 minus u to some gamma, which gamma should be any number greater than 1/2, we get that in fact we get the asymptotic behavior of this sigma. It's some constant divided by sigma square as sigma goes to infinity. And this constant depends on this function f. In fact, we have an explicit explicit expression for how to identify this constant, and this constant is finite. So what we get here, you see this function maybe looks like u to the gamma, where gamma is maybe less than 1. So it's a non-Lipschitz function near 0. And the noise, okay, so has dramatic effect on all this, that it's finite, and moreover, it behaves like constant over sigma square when sigma goes to infinity. And one can easily check by having our expression that whenever f of u is u times 1 minus u, cf equals 1, and this verifies Conlon-Doring conjecture. In fact, this was the motivation for our paper. In fact, we started studying just the case of f of u equals u times 1 minus u, and then we somehow realized that we can do it for much larger class of functions which are not FKPP class. The only requirement is this one. Okay, this is for large noise. And then you ask, okay, what happens with this equation when? So this gives asymptotics for the speed when sigma is getting large. What happens with asymptotic for the speed when sigma is getting low? Okay, and here and this is the result with Clayton, Barnes, and Zhenyao-San. We realized that we can get the asymptotics of this equation when sigma also getting smaller. Okay, what's going on? Suppose now again fu is non-negative, continuous, and bounded by square root of u times 1 minus u, the same condition we had in the previous paper with Karl and Lenya. And then we make the solemn assumption that fu over up, lim inf of this ratio is greater than 0, and lim sup of this ratio is less than infinity. So around 0, fu behaves like u to the p for small u. Okay, and it turns out that our speed of propagation of the front of this equation, in fact, behaves like sigma to some negative explicit power. So the power is here, -2, 1 minus p over 1 plus p. So, and we have constant C1 and C2 multiplying the same expression, but the moral is that V sigma behaves like this in the limit. Okay, one thing, it's not surprising that the speed, okay, the speed diverges. As sigma goes to 0, the speed diverges to infinity. So V of sigma goes to infinity as sigma goes to 0. Okay, and it's almost clear, since whenever sigma is 0, we're again getting back to our deterministic stochastic KPP equation. And in this case, we know that the speed is infinite. So the main message here that not only we know that it goes to infinity, you know how fast it goes to infinity, and it's like sigma to some negative power. And I have a couple of minutes, and the only thing I want to say is how one can think about heuristically about this result. Again, one can get that this noise term beats this non-Lipschitz drift whenever u is small. And how small you should be smaller than sigma to some positive power. I don't get to this. It's not very difficult heuristic argument to show why this should be the power. And that's why one can compare this equation again with the deterministic one with the cutoff. So again, the drift works only for u greater or equal than some small sigma to a power. And the speed of this equation, we can think about, again, we know how to at least asymptotically to think about the speed of the non-negative equation of this equation with cutoff. It should be the square root of the derivative of the drift around this point, and this gives you exactly the right order of the speed for small sigma, so as required by theorem 3. So again, we can compare this stochastic equation with the deterministic one. And the last slide, what can be the open problems? So we don't, unfortunately, whenever f is not is not in KPP class, and even for some question in KPP class, we don't know the RT over T. The left edge of the support has the same speed of propagation as the right edge of the support. This kind of open question, which is we believe so, but this has to be verified. We don't know for some weaker conditions on FU, so we know that our result holds when gamma is greater or equal than 1/2, but what happens in the case when gamma is less than 1/2, whether this we have the same type of results. And suppose we know that lim of fu to the over up exists, can we show that C1 equals to C in the theorem 3? And we also, which means that there exists a sharp asymptotic up to the constant of V sigma. We also it's also a very interesting question whether we can match the upper and lower bound on the speed propagation. Okay, I guess I'll stop here, and many thanks for your attention.
So thank you very much. I think we move directly to the discussion, and so the discussant for this talk will be Bernard Derrida. Are you able to share your screen?
Okay.
Yes, okay. So thanks.
Okay. First, I want to thank you for inviting me to talk here. And I also enjoyed very much Leonid's talk. And what I'm going to mention are some aspects of the noisy Fisher-KPP equations on which I worked with Eric Brunet, Al Muller, and Stéphane Munier some years ago. You see, most of what I'm going to say are rather old works. And so I'll mention some work with Damien Simon, and the main part of the talk will be on joint work with Zhang Xi. Okay, so I will discuss three aspects. One is what kind of model, in what kind of model you have behaviors like the noisy Fisher-KPP equation. Then I will discuss fluctuations and large deviations. And so this is the work with Zanchi. And then I mentioned the wall problem, where there is no noise, but which has a lot of similarity with the noisy equation. Okay, so as we have heard, this is a Fisher-KPP equations up to the 1/2 factor that is not present here. It's written here, so this is a white noise there. And the questions you can ask is, what is the velocity? So we have heard about how the velocity depends on the noise. Here the noise is 1/√n instead of being sigma, but how the velocity depends on the noise. But the questions that we tried to study many years ago with Eric Brunet in particular was to tell also the position of the front will fluctuate and how it diffuses. So what is the diffusion constant of this front? And the answer that we had is the following, that you see, for the velocity, the first term is, I hope you can see the bottom of this slide, is that it's one, is it visible, the bottom, or the formulas down there? Or?
Yes.
Yes, okay, so there is this pi squared, because on my screen it is not, but there is this pi squared over log squared n there, and then there is an additional term also due to the noise, which seems to be universal, which is log n over log n cubed. So this is the red part was predicted or conjectured in a work with Eric Brunet in 1997. Then we pushed further the analysis and our analysis, and we got the next term for the velocity plus also the diffusion constant, which is also like 1/log n cubed with the known coefficient. And as far as I know, so far only this velocity has been understood from a mathematical point of view, as was mentioned by Leonid just in the previous talk. But as far as I know, the diffusion constant is not yet known, and I think it has been there for a long time, and it would be very interesting to say something about the fluctuations. Okay, so now let me come to models where the Fisher-KPP equation appears. And as we heard, there is this reaction diffusion problem that the particle is diffusing, and then at a certain rate it splits into two particles. So this is a branching Brownian motion. And if you add to it with a small rate, the possibility that two particles which cross will coalesce, then you can prove, or you can show that it is related, it is a realization of the noisy Fisher-KPP equations. And in fact, for the lattice version, this was shown by Derrida, Müller, and Smereka about 15 years ago. Now, there are other realizations, which I am going to mention here, is the n-branching Brownian motion that essentially we worked on with Brunet, Müller, and Meunier, and also the LBBM. So let me tell you what the NBBM is, n-branching Brownian motion. Imagine that you have you start with one particle, but you could start already with n particles if you want, and these particles diffuse and they branch like in a branching Brownian motion. So this is a branching Brownian motion. A full branching Brownian motion would be this full red picture. But now in the NBBM, you introduce the rule that the population cannot become larger than n. So there is at most n particles. In fact, it will saturate at n. And when you have n particles, it will remain at n. And the rule is whenever there is a branching event, then the leftmost particle is erased. So if you try to draw a picture, this would be just a regular branching Brownian motion. Here, a particle starts and then branches and so on. And then in the n branching Brownian motion, then because you eliminate the leftmost particles each time there is a new branching event, then you have this blue this blue population as a function of time. And the question is how, for example, the velocity of these blue particles, how it depends on n, for example, how it fluctuates with n, and even a question about large deviation. So this is the n branching Brownian motion. Now, the L branching Brownian motion is a slight different version, is that you start with a branching Brownian motion with a single particle, and the size of the population grows. And then you have the rule that there is always in this population a leader. Let me call the position of the leader x1 of t. And whenever a particle is at a distance larger than L from the leader, it is erased. And again, you expect the velocity, the diffusion constant, to be given by the formulas that I mentioned earlier, except here the way the L is related to the noise would be L of order log n. So these are models. Now, let me come to the results that we obtained with Zhanchi on this problem. And the question we asked was about not only the velocity and the fluctuations, but large deviations. And here I am going to discuss only large positive deviations. So what is the probability that if you take the n branching Brownian motion, or L, or this coalescing branching Brownian motion with this reaction diffusion, that the rightmost particle is at a position Vt after time t. So if you just take the BBM, the answer to this question has been known for many years, for more than 30 years, by Chauvin and Rouault. And then the probability that the large deviation forms, the probability that the leader of a branching Brownian motion, so without noise, without the saturation, is just exponential t v minus v squared over 4. And the question we asked with Zhan was to say, what happens if we introduce the noise, in the sense that we take the n branching Brownian motion or the L branching Brownian motion? And the result is that the probability of having the leader at position V is a new, it's a new large deviation function. It's not the same as the BBM. There is a correction, and we try to understand this correction. And the picture is the following. The way of reasoning and the proof that we had is based on the following picture. We take a full Brownian motion, but when you go to the NBBM or LBBMs, some branches will be cut. They will be cut because sometimes a particle is too far, or some particles have been erased. And the question is, what is the chance that the particle which reaches the position Vt has not been killed by the erasing procedure? And how is it erased? The way it is erased is that a particle moves up to position Vt, but it could happen that, say, if you take the L branching Brownian motion, that at some stage in the past, then there is a subtree here which went sufficiently ahead of it to kill this red trajectory. So this is the main reasoning that we had. And using that, we could prove the following thing, that if the velocity is between 2 and 3, okay, here it's 2 would be the square root 2 of Leonid's talk, but if the velocity is between 2 and 3, the difference between the large deviation function for the LBBM and the regular BBM is of order L to the V minus 2. And if V is larger than 3, it's a different exponent. It's rather strange that the two exponents are different when you vary V, but this phenomenon, we find it in all these three cases, that is the NBBM, the coalescing random walk, and the NBBM. There is always two regimes. And one regime is just that how is it possible that the red particle is erased? One thing is that just by fluctuations, this red particle made the fluctuations which was to the left, and then it was erased by the subtree. So this is the red particle slows down somewhere in its trajectory, but the subtrees do not do anything special. And the other range is when the red particle slows down, but the subtree makes an effort just to be ahead of the red particle to kill it. So this is the kind of formula that we get. And we have similar formulas for the coalescing branching Brownian motion, where the exponents are different, but essentially we have these two regimes. And again, in the NBBM, again, we have these two regimes. So this is the main results that we obtained with Zanchi a few years ago. Now, let me, before I finish, I want just to mention very briefly, you remember that when I talked about the velocity, then there is this term minus pi squared over 2 log squared, and there is a term log n over log n cubed. And to my surprise, you see, when we wrote first these terms 15 years ago, I thought that this was really the effect of the noise. And to my surprise, in fact, you get these two corrections of the velocity in the problem of a wall. So you take a branching Brownian motion. Now there is no noise, the equation has no noise, and you just eliminate all the particles which cross a wall moving at the velocity v. So this is the wall here, and so the survivors are these blue particles. So the red would be the full Brownian motion, branching Brownian motion, but this is the blue part. So after a while, this is the population. And then you take the red, the Brownian motion, branching Brownian motion by itself would move at a velocity vc, and the wall moves at a certain velocity v. And now you ask the following question, so you want to condition on the following thing, that the total number of particles is 1 at time 0, and you condition on the fact that time t, it is again 1. So what happens is that the population, the size of the population grows for a while, and then essentially fluctuates around a certain value here, which is, we call the number of particles the quasi-stationary number of particles. So you have a kind of stationary regime here, and at the end it comes to 1. And one can estimate that the number of particles in this regime behaves like exponential pi v critical minus v. V critical would be 2 in the case of a branching Brownian motion. Now, when we computed that, we could calculate this n sufficiently with sufficient accuracy, because this is a non-noisy equation. And then when we inverted v versus this average n, we recovered this formula. So somehow these two terms do not seem to depend on the fact that there is noise. And to me, it's a surprise. Now let me just finish. And you see, as far as I know, you see, certainly I don't know all the mathematical literature, but I don't think even the diffusion constant is understood from a mathematical point of view. For the large deviation, we have only one bound, and I believe that the n dependence or the L dependence is the correct one, but we have only one bound on it. And there are a number of problems which are related, which I did not mention, which have to do with genealogies and in fact, directed polymers, because in fact, my first interest for this kind of problem, it comes back to 30 years ago, because I was interested in the problem of directed polymers in a random medium, but in high dimension. And this problem is very related to that. So thank you for your attention.
So thank you. I guess we open up for for general questions or.
So I have a question for
Yeah.
Leonid,
Yeah.
because you see there is this right and left point of the support.
Yeah.
And is it known, for example, when the noise goes to is very small, what is the statistics of this distance between the two? So you have an interval which is, I guess, fluctuating in time, and okay, so this is a question. In fact, I have tried to work a little bit on it, and I wonder whether there is a prediction for it. For example,
I guess we don't know. We even don't, okay, as I say, we even don't know when we move from this binary branching Brownian motion, we don't know whether as time goes to infinity, whether the interface remain close. So whether so we know that for the regular case, u time 1 minus u, which corresponds to branching Brownian motion with coalescence, then so in this case, what do we know? We know that, okay, the only thing we know for sure, okay, if there is no drift, then there is stochastic boundedness between the right and left points as time goes to infinity. Whenever we add the drift, we don't, I don't think it's known what happens as time goes to infinity.
But if you have no drift, you can tell what is the distribution of the size of this region?
Yeah, if there is no drift, then we know that as time goes to infinity, you will get something which is bounded. And we know, so it was in the papers of, as far as I remember, of Roger Tribe and Carl Mueller's many years ago, and they found there is no first moment. The expectation of the expectation of the difference, so goes to infinity.
Okay.
It remained bounded, but only with moments which are less than 1.
Okay.
Okay.
So you said, okay, maybe I'll send you a message to have the precise reference.
Yeah. I send you. This is very interesting, but so that they know that as time goes to infinity, if there is no drift, so it remains bounded with the first moment diverging, but it's bounded. All the rest is completely we don't know what's going on. We don't know what's going on when we add the drift and we move to the KPP scenario. And it's very good questions how as epsilon you say goes to 0, what happens with the statistics of right minus left, so which should increase, but we don't know how. Yeah, it's very good question. Yeah, we don't know. Yeah.
You see, there is a similar question. Okay, I'm sorry, maybe you should interrupt me if you want, but you see, lots of people have worked on if you take the branching Brownian motion on the tip, on the particles close to the boundary. Now, when you go to the NBBM or things like that, how is it affected? Because what happens at the tip controls the velocity. So how the measure near the tip is affected by the noise or the N large for the NBBM. So
we don't know. Yeah, exactly. It's again, it's a great question. We don't know. Yeah, since how you can also add coalescence. I'm pretty sure you'll have the same effect on the tip, on the behavior near the tip. Yeah, and it's more or less the same class. So when you add N Brownian motion, or L Brownian motion, or coalescence in the system, so you somehow bring down a little bit number of particles, yeah, we know. I don't think we know. No. And I have also a question to you. Do you have prediction for the next storm for Vn? You have this log n over log n cube. The next, which will be 1 over log n cube. We don't have it's not known.
No, I don't know. Maybe Eric Brunet knows. But
I get it. Yeah. Okay. Since the next term is clear, would be very interesting also to see what's going on there. Okay. Thank you very much. I really enjoyed your talk.
okay.
All right. I think we have time for one quick question, if there is any from the rest of the audience. There seems to be nothing in the chat, but does anybody want to question something or comment something? Mario?
Justin, I'm not sure it's a short question. So
Okay.
you said, I mean, maybe we can postpone. At some point, you said that the noise wins for a small u against the drift. And I was wondering, what's the idea if there is a short...
The idea is that the noise creates a martingale, and you have a non-negative martingale. Whenever you have this drift, which produce a little bit mass, but so if it's not enough mass there, then the non-negative martingales brings you down to zero. That's more or less the whole idea. And this non-negative martingale is related to critical branching process. And critical branching process, we know, dies out. So and this is there. So one can think in terms of critical branching process. Whenever you start with small mass, you die out very fast. That's what we mean by that fact that noise beats the drift. And if drift doesn't create a lot of mass, then this critical branching effect kills this mass. Okay. And this is what creates this comparison with the equation with cutoff.
Thanks.
Thank you for the question.